All right, so at a couple of requests, I'm going to work questions number 13 and 14 from chapter 4 of our Tsokos textbook. All right, so here we go. The graph shows the displacement of y of the particles in a medium against position x when a longitudinal wave passes through the medium from left to right with the speed of 1 centimeter per second. This is the displacement at time 0. State what is meant by a longitudinal wave pulse. All right, so that's the first thing they want us to do. They want us to talk about longitudinal. Well, remember, longitudinal, the big part of longitudinal is that the particles vibrate back and forth parallel to the energy propagation. Okay, and that's the big thing. You have to include that word parallel, right? In longitudinal, the particles are moving back and forth, and as that particle moves back and forth, the energy of the wave moves parallel, either to the right or left. You could have it going up and down as well. If the particle is vibrating up and down, then the wave could be moving up or down just like that. All right, so that's the idea behind a longitudinal wave pulse. All right, so the next part of this question is the diagram shows a line of 9 molecules separated by 1 centimeter. The positions shown are the equilibrium positions of the molecules when no wave travels in the medium. So for part I, we're going to copy the diagram. Okay, it's copied. Lovely. Good job, me. Immediately below the copied line, draw another line to show the position of these molecules when the pulse travels through the medium at t0. Okay, now that's what they've given us this graph up here for, is to tell us what is happening to each of those particles at time 0. All right, so let's go ahead and look at it. Recognize that this, remember, x is showing the position. So x0 would be this point right here. You can see it down at the bottom left-hand side of the page. x1 right here would be the one at 1, and then you've got 2, 3. Those should all correspond to the x's up here on the graph. Okay, now the y value, it said, was the displacement of those particles. All right, so we're going to go ahead and draw them. You could do it down, I guess we can go ahead and do it down below. All right, so here we go. The first particle is found at x equals 0 here. Okay, now we look up at the graph, and at 0, that particle has a displacement of 0, which means it's going to be in exactly the same place. So I'm going to do it down here at 1. Okay, that's going to be my I. Okay, so it hasn't moved at all. All right, the next one, particle at 1 here, if you look, let's see, each one of these lines, it looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each one of those is 0.05 centimeters or half a millimeter. So it looks like number 1 here is up at 0.35 centimeters. Okay, so that's a positive value, which means it's going to be 0.35 centimeters. So not quite half a centimeter, so not quite halfway, but it's going to be just to the right, okay, of where it used to be. Okay, so this is that particle. When at rest, when the air is not, or when the medium is not moving, it's there. But right now, because of the wave, it has a displacement of 0.35, so a little bit to the right. Okay, now the particle at 2 has this displacement right here, right, which is 1, 2, 3, 4, 5. So it looks like it's up at 0.75, so more than half of a centimeter over. So half would be here. It's got to be more than that. So here's my particle that used to be at 2. I'm going to go ahead and label these. This used to be at 0. This used to be at 1. This used to be at 2. All right. Now the one at 3 right here has a displacement to the right again, right? It's still positive of 0.35. So that guy is not going to be quite halfway. So here, there's my 3 right there. The 4, you'll notice, has 0 displacement, so we're going to put the 4 right where it was. So that's the 4. And then we'll look at the particle that would be at 5. So this guy looks like very similar to the other one, is going to have a displacement of about 0.35. But notice now that it's negative 0.35. It's down below. All right, so because it's negative, that 5 is going to move not quite halfway over. Okay, so about right here. So there's my 5. Okay, and then the 6, you'll notice, is all the way down here, which is at about negative 0.75, right? So he has to move, that 6 needs to go past the halfway mark to about here. So there's my 6. Okay, the 7 has moved to the left as well by about negative 0.35. So he's moved to the left, so he's right here, not quite as much. And then the 8 has no displacement, so the 8 is right here. All right, so there you go. Now we've shown what it looks like at time equals 0 as the wave passes through. Okay, now II asks us to indicate the position of a compression. All right, so the compression is where the particles are crammed together because they've been moved more. Now you can tell that it's got to be in this general area where the particles are packed up, they're being pushed together. Generally speaking, the point that we want to label is the point that's right in the middle of that, because chances are it's going to be more compressed in the middle than it is on the outsides. You may not be able to tell because of my estimations of where these points go, but hopefully that kind of makes sense, that the 4 would be the point of the compression. So that's BII right there. All right. Now, now it wants us to repeat the process to show the position of these molecules at t equals 1 second. All right. So now what we need to do is we need to complete the process over again, but a second later. All right. So we're going to go back up to the graph, right? And the first thing we're going to do is show what this pulse looks like a second later. Now, we're going to just use a different color up here because I don't have much other choice. It does say that the pulse is moving from left to right. Notice I didn't need this information before. None of it had anything to do with the movement of the pulse. It was just, where are those particles now? So now we're going to look at the medium is moving from left to right with 1 centimeter per second. So we want to see what's happening after 1 second. So if it's going 1 centimeter per second, that means that the pulse is going to move over to the right 1 centimeter, right? So it's going to be over here. This is going to be like this. It's going to go down, hit there. Okay, so all I did was I took that pulse and I moved it over. Note that over to the left here, right, it's 0. So it's going to be 0 up to that point. Okay, and I just moved everything over. If you need to go point by point and move each one over 1 centimeter, that's fine, right? Move this guy over 1, move this guy over 1, move this guy over 1, right? You can do that, and you can move each particle over 1 and then connect the dots afterwards, all right? So we've drawn what the pulse looks like. Now they want us to basically do the same thing that we just did in BI. In fact, not basically. They said repeat BI to show the position. All right. So let's go ahead and do that. Notice that the particle at 0 still has no displacement. So the particle at 0, let's see, where can I fit this? We'll just put it right above it. Okay. So the particle at 0 has not moved at all. Oh, it's not going to let me draw over there. That's not cool. There we go. All right, now it's going to let me draw it. So I'm going to draw it right here. So here's my first one, okay, at 0. Okay, the point that was at 1, notice that it also has 0 displacement now. So that guy is going to be here. Okay, the guy at 2, the particle at 2 is going to have this displacement right here, which is the 0.35. It's positive, so it's going to be over to the right. So this is 0, 1. So the 2 is going to be 0.35 over. Okay, so not quite halfway. The 3 is up here now. It's at the 0.75. So here's guy 3 used to be here. He's going to be over there. Okay, the 4 right there has a positive 0.35, so somewhere around here. Not quite as far as the 3 was moved over. Okay, guy 5 right here has 0 displacement. We can see on our graph, so the 5 is going to be right there. The 6 right here now has a negative 0.35 displacement, so he's going to move over to the left just a little bit, like that. 6. The let's see, the guy right here, 6, 7. The guy at 7 has a bigger displacement, so 7 is going to be all the way over here. All right, and then 8 has a negative 0.35, so he's not going to be quite as far. There we go, and you can now see what's happened with each of the particles, right? Now, one of the things that it wants us to do is comment on the position of the compression. Well, you'll notice that the compression, which was here, has now moved over to the right. Even if we're looking at the thing as a whole, it's very clear that everything has shifted over to the right. Okay, now the medium itself hasn't, right? I still have the same amount of going right, going left, all those other things that I used to. But the fact is that the compression, which is the transference of the energy, we can see it very clearly with the compression, that has moved over. And so it's now at this position. The center one would be 5 there. All right. So hopefully that made sense, and hopefully that looking at how the graph works helps us to identify where those particles are going to be now. All right. Okie doke, let's go ahead and move over to the next slide, which is question 14. All right, so this will be, you know, a similar idea, still trying to look at those same principles. All right, this graph shows the variation with distance x of the displacement y of air molecules as a sound wave travels to the right through air. Okay, so this time the medium is air, it's sound, it gives us positive displacement, that means motion to the right. Remember, sound is a longitudinal wave, so this connects with the last one that we did, particles bumping into each other, and it gives us the speed of sound in air is 340 meters per second. And the first thing it asks for is the frequency of the sound wave. All right. Well, without doing too much work right off the bat, you know, one of the most common formulas that we use is that the velocity equals the frequency times the wavelength. They gave me the velocity, right? And then they want me to find the frequency. So really, if I can find the wavelength, then I'm good to go. And lo and behold, they did give me a picture that is going to help me get the wavelength. Okay. Now, one of the things is this is asking about the frequency of the sound wave. Okay, so that's the wave as a whole, right? And so when I look at that, I see the wave here that goes from negative 0.010 at time 0, and then it goes up, and it comes down, and it completes one full cycle after 0.4 meters. All right, which that means that's going to be our wavelength. Okay, don't get confused with this over here on the side, because it can be confusing because there's a distance over there as well, but that is not the distance that we're looking at, right? Though that's actually the distance that the particles are moving, right? That's the displacement y of the air molecules. So that's the particles moving. We aren't interested in the particles right now. We're interested in the sound wave itself, all right? Which the speed of the particles is completely different. They're not going at the same as the speed of the wave, right? We always have two different things that we're considering. One which is the wave itself, and one which is how are those particles moving within the wave. You can look at the I showed some of this in a video once. You can look at that to visualize the particles moving and how their speed is different from that of the wave. I believe that Cognity also has a very good animation in this section in which it shows the particles moving back and forth at one speed and the wave, the compressions of the wavefront moving forward at a very different speed. All right, so we're going to go ahead and put that in. We've got 340. This is in meters per second, so that's what I want. I'm solving for the frequency, and the wavelength is, they were very nice to us. They gave it to us in meters here. If this isn't meters, you should change that before you put it into your formula. We definitely always want our stuff in SI. All right, so I'm going to go ahead and solve this. It's going to be 340 divided by that 0.4, which should give me then the frequency, and I get a frequency of 850 hertz. All right. Now we go on to letter B, which says state a distance x at which a compression and a rarefaction occurs. Now, if you think about the previous question, and if you memorized or if you kind of have seen enough patterns, you might be able to get it without doing any work. All right. If you can't, then we can do basically the same thing that we did in the last question and see if we can identify what is happening to each of the particles in this scenario, right? So let's draw our number line just like we did in the previous question. This is one reason why that previous question was good, is because it teaches us, okay, so I'm going to have a particle at 0, a particle at 0.1, a particle at 0.2, a particle at 0.3, and a particle at 0.4. So I'm just going to look at these 1, 2, 3, 4, 5 particles. If I need more, I can go in and get more, okay? But if I can do it with less particles, with less work, then I'm going to obviously do that. All right, so at 0, we see that the particle that used to be here has moved over to the left, okay? So the green marks here are going to represent where they originally were, okay? And hopefully that's more or less in the right position, okay? So the one over here on the left, the 0 has actually moved over to the left. So I'm just going to put it about what would be about half the distance from one to the other. The distances are not super important. What's important is what we're seeing. Okay, the particle here at 0.1, right, this guy right here is where it's supposed to be. Okay, the particle at 0.2 has moved over to the right. It has a positive displacement, so we're just going to place it to the right of where it would have been originally. Okay, the 0.3 is not moved, 0 displacement, right? We can see that right here. And then the 0.4 particle has a displacement of a negative displacement, which means that that particle is moved over to the left. Now, again, it doesn't matter how far you move them, but we are seeing what we want to see here, right? And that is, we can see the compression and the rarefaction. Right here, you can see that the points are closer together than they used to be. In that case, it's a compression, and we would say that the compression occurs at the center point, which is 0.3 meters. And so that would be the answer to BI. Okay? The rarefaction is the place where they're more spread out than they used to be, right? And you can tell this particle moved away over to the right, and this particle moved away over to the left. Therefore, the particle that's in the center, the one that's here at 0.1 meters, is the one that is in a rarefaction then, because it's at the center of that spreading apart. And so therefore, we've answered question B. All right, so hopefully that was helpful. If you have any more questions about these, please do let me know. I'll be glad to help you out and answer those questions as they come. But this is a common type of question on IB exams, both in multiple choice and free response. So get comfortable with these types of questions and get comfortable with this thing that we did down here at the bottom. Remember how we drew our number line and we simplified it. You don't have to include every single point. You just have to include enough that you can get the general idea of what's happening there. All right? Well, that is it for this question, and we are done with this video.